Hello again, and welcome back to the intermediate track of Beam College for 2023. This is session 4, and I'm Dr. Carrie Downey Clark, and I'm going to be helping you go through the actual pipeline code in this session. So if you remember, there are these 6 parts that we're going through for the intermediate track this year, focusing on machine learning pipelines in Beam. And today we are ready to dive into our example pipeline code. And we're going to separate this into 2 parts because it is all on the complex side, but that's because we're trying to do something complex, and that's where Beam can really shine. So today we're going to cover the first half of our pipeline. And just to remind you, the pipeline takes as input help center phone calls in the wave format. It uses a machine learning model to move that voice data to text, then uses a classifier to say what kind of call, what's the user trying to do. Then based on the kind of call the user has, we're sending it to an LLM. In real life, this would be an LLM fine-tuned for that kind of request. But for these example purposes, these are just random small LLMs I selected. Finally, the output of that LLM is text once again. And so we send that to another model to transform the text back into speech and save it as a WAV file. The idea being that that could then be returned to the customer. So today we're going to cover the initial input, the voice to text model, and the classifier. So for this, it's much more useful, I think, to look at code instead of slides. So we're going to Colab, and I'll be using a Colab notebook that I will also make publicly available at the end of the course. So here we are. In the beginning, as ever and as always, we have to install our dependencies. We're trying to keep this fairly lightweight, and so we're installing the dependencies that we need and no others. You see it's a fairly short list. Next, we have a statement to basically connect this Colab instance to our actual Google Cloud identity. We need to do this to read the input files because they're held on a GCS bucket. That just makes it much easier to use here in Colab. The bucket does have public access permissions, so for this authentication, anyone can do this and then access those files. Of course, like any Python program, we have all of our imports at the top. These will make sense as we go through the code. You'll see where we're using these different classes and methods. Okay, on to the good stuff. So first off, we are using data. And the data that we're using here is from a project that is free and available to everyone that was constructed as a way to give people a chance to develop machine learning models using fairly realistic voice interactions between a fake customer for a fake bank and a fake teller or a fake employee at that bank. Something that's very nice about this data set for our purposes here is that it has the actual human speech. It is asking for structured information, so we think we can make a good, strong classifier for it. And all of the data is present, including transcripts and labels for the types of call. And this makes it much, much easier, of course, to train our classifier. And I'll talk a little more about that in a moment. But if you're wondering, where does this data come from? Am I using actual bank calls? Nope, this is all fake, but it is fake in a realistic way. So that's where our data comes from. The first step is taking those files, the WAV files that we're going to read, and transforming them into speech. So here we're using our Hugging Face pipeline model handler that we mentioned in the last session. The Hugging Face pipeline model handler is very powerful and surprisingly simple. I know which model I want to use, the OpenAI Whisper Small model. And when I go to that model page here in Hugging Face, I can see up here a place where it says use this code in transformers. That's always the first place I go if I'm looking to use a model with the Hugging Face pipeline model handler. Because when I click that little transformers block, I get this pop-up and it tells me how to use the pipeline with this model. They define this, of course, with the pipeline construct as though you're calling it from inside a normal Python program using Hugging Face pipelines. But a nice thing is that this gives us all the information we need to instantiate that Hugging Face pipeline model handler. This is the task that is a required argument for the pipeline model handler, saying, what are you trying to do? Here we're trying automatic speech recognition. And it also gives you the model identifier. And I'd just like to call attention to the fact that this pipeline can be defined in one line here. And alternatively, you could load the model, but when you load the model, you also have to usually load the processor or a tokenizer, and you often have to process your own data. The pipeline, notice that though it can take a tokenizer argument, that tokenizer argument is almost never needed because the pipeline knows what is the default tokenizer or processor, what you would get when you do this from pre-trained call. The pipeline will always get the right one if you're using the standard tokenizer or processor, and that can greatly simplify your code. In fact, back here with our model handler, we can see that we needed exactly those values. The task, which is automatic speech recognition, and the model, the Whisper Small model, exactly like if we were making the pipeline as a Hugging Face pipeline construct. I have some additional arguments here. One, because this collab can have a GPU attached, I say device should be GPU. The code is smart enough to know that, of course, when there is not a GPU, it will fall back on CPU. Even if there's no GPU, the code will not fail. It will try to run on CPU using system memory. I give a minimum batch size of 2 to try to make this more efficient. Running locally, this is about the biggest batch I can do in this Colab instance. In real life, depending on your compute resources, you can get much more efficient processing, particularly on a GPU with a larger batch size. But notice that it's the minimum batch size I'm specifying. The pipeline model handler will also dynamically adjust the batch based on performance. And so you can set the minimum size to kind of get to a higher batch size more quickly, but the model or the pipeline will automatically adapt. And that's one of the big advantages of using our model handlers. I also say this stanza, load pipeline args, because I am giving data that is often more than 30 seconds long. And the Whisper Small model specifies that, let's see if we go down here, it's designed to work on audio samples of up to 30 seconds in duration. If you naively give the model more than 30 seconds, it will fail. But another big benefit of using the Hugging Face pipelines and pipeline model handler is that they make the chunking, breaking a longer piece of sound file into smaller chunks and reassembling it they make that automatic. And so that's where we get this chunk length s equals 30 parameter that we're passing to the pipeline. You'll notice that that's in this load pipeline args stanza. So this basically accepts a dictionary of quargs that would be passed normally into the pipeline. We also can accept quargs that are passed into the model, the inference args argument, although we don't need to use that in this case. We're just using this pipeline arg. And finally, we say large model is true. This is not actually a very large model, but this is relative. And it's saying, don't try to load more than one copy of this model into our GPU or CPU. This is something that's very important when your model size is close to your VRAM when you're using GPUs, for example. But if you have a very small model, it may be more efficient to load multiple copies of the model so they can process in parallel. So I find a large model is true is what I'm often using because I'm often using large models. The Hugging Face pipeline model handler is what we use for our inference call. But we also define a post-processing function that we're going to use with this model handler. This takes as its input a prediction result, because all of our model handlers will yield a prediction result. Of course, that prediction result is more rich than just the output. So if we are looking for the text output of the inference, what I want to do is say that the result will become equal to the inference component of the prediction result. I just take the first item, and then I'm going to take the text value out of the dictionary that is returned by the Whisper model. So it can be a little confusing, honestly, when you're writing a pipeline. Where is the thing you want to pass to the next pipeline component? I recommend when you're writing your pipeline to write it locally and develop locally so that you can print out these prediction results and the items that are inside the inference, what actually is returned from the model. Often it can take some exploration of that data to learn what you really need to do to get the single or multiple items you intend to pass on to the next part of the pipeline. Here, it's a little odd, but I'm returning the result twice. So I'm returning a tuple of 2 copies of the result. This is because I am going to use a keyed model handler next as the classifier. And a keyed model handler just means a model handler that takes a tuple of a key that it will also emit the same key with its output and an input. So the keyed model handler takes a key and the input, uses that input for inference, then it will yield the key and the prediction result for that input. So the important thing here is this lets you pass a key through the transform, keep it associated with the inference output so that you can consume it later. And in fact, as we go to the classifier, you'll see why we often want to do that. It's a fairly elegant way to get around a problem that we often have with a machine learning pipeline in particular. So this is all the code we need for the initial part. We just need the model handler and the post-processing that prepares the data for the next step of our pipeline, or for output if we were finished here. Next, we're looking at the classifier. Now, you've seen that when I want to do something, my first stop is to go to Hugging Face, click on the models page, and see if there's a model that does what I want. Classification, however, is often a problem that involves building a classifier unique to your domain on your own data, and likely updating that classifier on a regular basis. XGBoost is a very powerful way to build a classifier, and it's something that is also probably one of the more complicated ways, as you learn it, to build a classifier, particularly when you're using something like text, when your data is not only categorical or numerical, when you have actual free text. Then the XGBoost classifier starts to involve more manipulation of the data. And again, it can get fairly complex. So we're not going to dive deep into that because this is a Beam college, not an XGBoost college. But I've put some links here where there's a Kaggle notebook and then also just an article going into depth with code samples on how to treat text and text classification with XGBoost. You may want to read that to get some more background on things like the vectorizer and dimensionality reduction, the LSA. So, because I have to train my own model for this, I also have to train my own vectorizer that fits my data, and I have to train my own function to reduce that output of the vectorizer, which is a matrix, to a single dimension, so that I can use that as input into my classifier. This is something that, like I said, is beyond the scope of this talk, but I just want to highlight that I have to then save in my offline process where I was training this. I have to save my vectorizer and my SVD, the function I use to reduce the dimensions. I have to save them after I've fit them to my data, because that is how I use them to train the model. And I need that exact already trained fit vectorizer and dimension reducer. Otherwise, my classifier will not work like it did in my training. So this is an important point. And here I've saved them as pickle files, and I just load them. I had to upload these files into the Colab, and I load them directly here. Then I define the XGBoost model handler. As I say, this is not something I can just download. I had to make my own. And so I had to save the model with its model, save model functionality locally, upload it into Colab, and now I provide that local file as the model state. And the XGBoost model handler knows how to use that local file. In an earlier series, I said we were going to use the XGBoost model handler pandas. However, I found for these audio processing tasks, enough of the libraries use NumPy that I wanted to use the NumPy handler. So that means that the XGBoost model handler is going to be taking NumPy inputs and giving NumPy outputs. Then I wrap the XGBoost model handler in a keyed model handler. And the keyed model handler works like this. You just give it the model handler that's specific to your framework as its constructor argument. And the keyed model handler, oh no, reconnect that runtime. The keyed model handler simply wraps this and allows us to pass a key in along with our input, and it guarantees that same key is emitted matched with the inference output corresponding to that input. So it gives us a stable key that passes through the transform. But other than this, you need to know that when you have a keyed model handler, the input and output are now a tuple of key and input, or key and output. So because this is the next transform in our pipeline, that's why back at our post-processing whisper function, we emitted the result. This is the text that comes out of the speech-to-text model. We give it twice because we want to keep that original text as the key. The other copy of the text that's input to the model is going to be converted in our pre-processing. Before it gets into the model, we're going to transform it. We take the element 1, right? It's taking as its input that output, a tuple of two strings, the result and the result again. I take the second one, which is the input, element 1. That's going to be the call text, what the people said on the call. Now I vectorize it with my vectorizer. Then I reduce its dimensions. And then finally, I'm going to return the same thing, the same key as my key to pass into the model. Remember, it's the pre-processing. And then I also give that vectorized, dimensionality reduced representation of the same text. That goes into the model. The model performs classification, and it will emit the class. Because the class is a categorical, it will emit it as a number. And of course, when we're training, we set up those categories. And there are basically 8 different types of call. Check balance, get branch hours, order checks, pay bill, replace card, reset password, schedule appointment, and transfer money. And when we trained our model, we represented these as 0, 1, 2, 3, 4, 5, 6, and 7. So as part of the post-processing, we have to map those output values, which are integers, back to the type of calls, replace card, schedule appointment, that we want to use for our next operation. And we could keep this, honestly, our next operation is just going to match a class to a model. We could keep it as numbers, but I feel like it's a clearer way when you're debugging or when someone else is trying to extend your pipeline. It's clearer if you're operating with the actual labels in text as opposed to operating with integers that map to those labels in a way that is easy to forget or lose. So I recommend doing it this way, keeping the text label as the output instead of the number of the class. So here, this is our post-processing. We take that original text, still element 0. We still got our key here and our result here. The original text is that element 0. The inference results are element 1. We're going to transform the inference results into an actual text representation. This actually returns a zero-dimensional NumPy array, and that's not what your next call is going to want to use. It will want a string. So we get this call type as array dot item. So we get call type as a zero-dimensional array here, and we just pull out the item, the actual string from it here. And we're going to return the call type and the original text. And that's our tuple going on to the next element. And the next element is going to be where we do matching the kind of call to a different model to perform further inference. But we'll get into that in our next session. So now back to our slides. So the next session, we're going to do a deep dive into our pipeline example continued, part 2, where we'll investigate the fan out, where each class is assigned to a different model, and then the execution of text back into speech. And we'll try to run the whole pipeline and look at it. I'll look at the actual pipeline code as well. Thank you all very much. I hope to see you virtually again soon. Have a good day. Bye-bye.